Hello, and welcome back to EECS 367, Introduction to Autonomous Robotics, and Robotics 320, Robot Operating Systems, at the University of Michigan for the winter 2022 semester. This is now our 14th lecture, the topic of which is going to be on configuration spaces. So this is how our robot operating system can represent the poses and the possible poses of our robot within a well-defined space. And so before we get started today, I will go ahead and minimize myself so that we can all see the slide content. All right. So to get started, the illustration on this slide is actually a nice conceptual diagram motivating this idea of configuration spaces. And in particular, what this is illustrating is an example from the cartoon Transformers, where a sort of humanoid robot could emerge, could transform out of some other kinematic pose, for example, a truck. And so this kind of illustration is a nice kind of conceptual diagram that motivates this idea of configuration spaces, where what we want to be able to do for our robot operating systems is to be able to sort of summarize the set of possible poses that our robot could take on by defining a configuration space. So we sort of want to be able to enumerate all the possible poses that a robot, for example, the one shown on this slide, could take, such that it's a valid pose based on the kinematic structure. And so this will fit into our topic of motion planning, because it'll essentially be a way of representing for our algorithms what potential kind of paths within configuration space our algorithms should be considering. And so you'll recall from our last lecture that we were looking at a set of motion planning algorithms, in particular the bug algorithms. Right, so we were looking at bug 0, bug 1, bug 2, up to the tangent bug algorithm, which were sort of an interesting set of biologically inspired algorithms that would perform motion planning within a configuration space. And so in today's lecture, we're going to sort of explicitly define the notion of a configuration space, moving forward to more complex motion planning algorithms. So to recap from our last lecture, one of the important points that we brought up towards the end was we made a few distinctions between the different motion planning algorithms that we had been looking at. And so in particular, one of for the set of the bug 0, bug 1, and bug 2 algorithms, one of the important pieces of information that we pointed out these algorithms relied on was knowledge of the robot's location within the space that it was searching. And in addition, we required that this space had defined some distance function that could be comparing the robot's current position to the goal position. And we also made the point that some of the earlier search algorithms that we had looked at in this course, for example, A-star search, used some additional knowledge that these bug algorithms didn't have access to or didn't require. And so in particular for A-star, the algorithm required a graph of the valid locations that the robot could take within the 2D space, and it also required the ability to build up this notion of a graph over the potential positions of the robot. And so this was this idea of a graph and being able to build up this graph over possible locations of the robot connects quite closely to the notion of a configuration space, which we're going to be defining more formally and looking at a little bit more formally in today's lecture. And so the goal and the sort of reason for our defining this notion of a configuration space is because coming up, we want to be able to look at a set of more complicated motion planning algorithms that fall into this category of roadmap search. So they'll still be very similar to the idea of graph-based search. And in particular, we're going to be looking at probabilistic roadmaps and rapidly exploring random trees in the next set of lectures for this course. And so this topic fits into the broader category of motion planning that we've been looking at throughout the course of this semester, where the algorithm would be expected to perform essentially search to find a path that our robot could take within configuration space within our robot operating system. So in last lecture, we looked at the bug algorithms, and earlier on in the semester, we looked at graph search. So the final two topics then that we'll be looking at towards the end of this semester will be roadmap search, and then we'll look at optimization-based search, for example, using gradient descent or potential fields. So
to start looking and kind of moving in this direction of roadmap search, the first thing maybe we could do is we could ask the question of whether or not our current search methods that we've already looked at, notably the algorithms that we looked at for 2D path planning, so the graph-based search algorithms, could be extended and applied to more complicated robots that exist beyond 2D space. So for example, would our 2D path planning algorithms be applicable to the case of an n-dimensional motion planning problem that might be required for a robot that has a kinematic structure like the Now robot shown on the right-hand side of this particular slide, so this humanoid robot. So to be able to answer this question, one thing that we should maybe look at are what assumptions our algorithm is making in the case of 2D path planning that we could then kind of think about whether they're still applicable and still possible in the case of this n-dimensional, kind of more complicated robot. So the first assumption that our algorithms were making was that we would have a known graph and that graph would be traversable. So in the case of 2D path planning, this was possible, where we could have a relatively small graph that would be traversable. But in the case of n-dimensional spaces, that graph is going to grow very, very large. And so not only does it bring up this question of whether or not it would be feasible to compute the graph in terms of traversing it, but in addition, it would bring up this question of how it is we could even construct and store the graph in memory in an efficient manner. Right? So that's one challenge of our current definition of graph-based search when we try and apply it to more complicated problems. But in addition, another potential issue is that our algorithms assumed known localization of both the map and all of the obstacles within the map. So when we try moving to these larger spaces, to these n-dimensional spaces, we have a couple of questions, right? So one would be how is it that we can detect collisions in these higher dimensional spaces? And in addition, how are we going to represent our robot within these spaces that would now represent a larger map? Would it still just be a point within the workspace, or would we need to potentially have a more complicated representation for our robot state? And finally, our 2D path planning algorithms also assumed known link geometries. But this doesn't consider the case where potentially the robot geometry actually changes as the configuration itself changes. And so all of these questions become challenges when you try and directly apply our 2D path planning algorithms to n-dimensional motion planning problems. And so these hint at the need for defining a configuration space that would enable new algorithms to be developed for these larger dimensional spaces. And so this definition of configuration spaces is what we're going to be looking at in today's lecture. So a configuration space, or C-space for short, it is going to be defined as the space of all possible configurations for a system, where for our purposes in this class, the system is going to be a robot's kinematic structure and kinematic configuration. So we've looked within robotics at two topics that have been using configuration spaces. So notably, all of our discussions of kinematics, where we described the geometry of possible configurations, and then when we looked at dynamics, which was how configurations of systems would evolve over time, including the possible incorporation of physics within the dynamics. Both of those topics were relying on some definition of a configuration space to be well defined. And so within a configuration space, a degree of freedom is going to be represented as one dimension of the space. So for every degree of freedom, you'll have a separate dimension within C-space. And so as a result of that, the span of C-space is going to be constrained by obstacles that exist within the world, or potentially joint limits that are defined based on the specific kinematics of a robot structure itself. And so the formal approach that we'll be using to explicitly define a configuration space is going to be based on the concept from algebraic group theory, which are groups. And so to look at this, what we'll do is we'll look at a set of examples, and we'll look at how the configuration space for different robotic examples is defined in order to build up this sense of C-space. So let's start by considering some examples of configuration spaces. So the first robot that we could look at is this Now robot, so this humanoid structure, which has 21 degrees of freedom, where each of the degrees of freedom is represented by one of the joints on the robotic structure itself, and each of these rotational joints could take on one of 10 angular values. So within this robot, we can then look at defining how many possible configurations there are. And so the answer in this case is 10 to the 21. And so the way that that's calculated is that there are 10 possible values, 10 angular values that each of the rotational joints could take, and there's 21 total rotational joints. So the total number of possible configurations would be 10 settings for the first joint, multiplied by 10 settings for the second joint, multiplied by 10 settings for the third joint, right, and so on for all 21 joints. And so this number of configurations would define every possible pose, right? So every possible configuration that our Now robot could take, based on this definition that we've looked at of 21 degrees of freedom, where each degree of freedom can take on 10 values. And so one conclusion we can take is that even this relatively simple humanoid robot has a very, very, very large configuration space, right? So 10 to the 21 is an extraordinarily large number of possible poses. And so this connects to what's known as the curse of dimensionality. So configuration space will experience an exponential growth in its size with respect to the numbers of degrees of freedom that exist within the space. Another point that we should point out is that in this particular example, we haven't considered any obstacles yet or joint limits. But if we were to incorporate obstacles or incorporate joint limits, these would become discontinuities or potentially nonlinearities within our configuration space. So let's look at another example that should be familiar. So let's consider a planar point robot that exists in some bounded rectangular world. And so now let's ask the question of essentially how many configurations are in the configuration space for this planar robot. So the first thing we could do is we can point out how many degrees of freedom there are, right? So the first thing we could look at, right, so there's an x-coordinate and a y-coordinate, or x1, x2 in the figure. So there's 2 dimensions in this space. So correspondingly, our robot would have 2 degrees of freedom that it could move about this space, right? But in addition, this space is not discrete. So this is a continuous space, right? So the robot could exist anywhere within this boundary. And so as a result of that, the number of poses that the robot could take on is actually infinite in this case. And so to define the configuration space for this robot, we use the group of real numbers R2, right? So it's the product of the 2 real number lines, and this defines then the 2 degrees of freedom that this robot could take. In addition, then we could look at another case that we're familiar with in our discussions of, for example, the Roomba robot, or we could consider like a Turtlebot, and we could ask once again, what's the configuration space of a Turtlebot where we've incorporated not just the planar x1, x2 coordinate in the pose of our robot, but we also have an angular component, theta, describing the rotation of our robot. So in this case, we've added a 3rd degree of freedom, right? So we've added that rotational degree of freedom to our space. But in addition, that rotational degree of freedom is a little bit different from just the planar x1 coordinate and x2 coordinate. And so the way that we can describe the resulting configuration space is we still have our x1, x2, so we still have R2, but we cross that with the space known as S1, which describes the group of one-dimensional rotations. And so this group S1 is also sometimes referred to as the one sphere, and can be visualized as a circle in 2 dimensions, as is shown on this slide, which represents the idea that every possible rotation about a single rotational degree of freedom is represented within that circle. So this on this particular slide, the circle that's illustrated with the various degrees of rotation is meant to convey that concept that the group S1 corresponds to these various rotations about a single degree of freedom. And that then hints at another important concept within these algebraic groups in the way that we're using them, which is that they correspond to transformations. So the group R2 corresponds to 2D translations, whereas the group S1 corresponds to rotations in 2 degrees. And so the Cartesian product of these two groups, so R2 cross S1, is what's known as the group SE2, where SE stands for Special Euclidean Group 2, where this group describes the group of homogeneous transformations in 2 dimensions. And so building on top of this, we could look at another example robot which we should be familiar with based on our earlier lectures, which is the planar arm robot that has 2 rotational joints. So I'd recommend pausing the video here, seeing if you can work through the number of degrees of freedom that this robot has, and then its corresponding configuration space based on the previous examples that we've been looking at. So I'll give you a chance to pause the video. So now that you've had a chance to think about this question, we can look at the answer. So the number of degrees of freedom should be familiar, right? So it has 2 rotational joints. So correspondingly, it has 2 degrees of freedom, which we could call theta 1 and theta 2. But then when it comes to the configuration space, there might be a number of different groups that we could use to describe it. So you might think R2 or potentially S2 or even S1 cross S1. And so it turns out that what we will typically use to describe a planar arm that takes this form is S1 cross S1, where this S1 cross S1 is actually a special group, which is known as the T2 torus group, where the T stands for torus, which has the special property that a space defined within this torus has this property where the space is fused on each degree of freedom wherever it reaches like basically 2 pi crossing over to 0. And so this torus, in the case of 2 degrees of freedom, can be visualized commonly as a donut, which is shown on this slide here. And it has this unique property where every single point on the surface of this torus is uniquely described by a particular setting of the 2 degrees of freedom. So that is a particular theta 1 value and a particular theta 2 value uniquely describes every point on that surface. And so we can think about the mapping of T2 to S1 cross S1. So within the figure on the right-hand side of this slide, it's illustrating this concept that the torus can be thought of as directly corresponding to the space S1 cross S1, which you can think about as being essentially a sort of plane, where it's defined. Every point in that plane is defined by a theta 1 and a theta 2, and maps to then a point on the torus's surface. And so more generally, Tn is a torus group for an n-dimensional system, an n-dimensional system, where essentially you have S1 cross S1 n different times. So we can build onto this T2 group to represent robotic arms that have additional rotational degrees of freedom. For example, in the case of the Barrett arm, it has 4 rotational joints if we exclude the finger grippers, and so correspondingly it has 4 degrees of freedom and can be represented with a configuration space defined by T4. Moving on, then, we can also look at robots that have not only revolute joints, but actually take positions within space. So, for example, in the case of a quadrotor helicopter, we could ask, what is the configuration space of a quadrotor helicopter? And so if we ignore the individual rotors and the instantaneous state of the rotors, which can be like abstracted away for the purposes of our robot operating system, then we could consider that the configuration space to essentially be a 6 degree of freedom configuration space. So the robot will take on some position XYZ and then some position RPY, so roll, pitch, yaw, denoting the orientation. And so These, as a side sort of tangent, these quadrotors have been really popular in the recent years. So this particular project from the University of Pennsylvania was a really cool application of quadrotors and the control that you can get with quadrotors. But I'll just point out that these robots have been really useful, have been really cool to see kind of grow in popularity. So recently you might be familiar with drone racing becoming a new sport. So I'll take a little tangent here and show this cool clip from the Drone Racing League, where essentially humans operate these drones and can fly them with really impressive manual control. So these robots are really impressive, and the human operators also are really skilled at operating these, obviously. And so typically the way that these competitions will work is that the humans would wear like a sort of virtual reality headset and then manually control the robots. So one way we could think about that is the humans are essentially searching through the configuration space, that 6 degree of freedom configuration space, in order to find a collision-free path throughout the environment. And so more recently, this has become an active area of research, in fact, for within the robotics community in terms of how to control these robots and these quadrotors specifically autonomously. So this particular clip is showing from the 2017 IROS autonomous drone racing competition, one of the competitors navigating through a map that's somewhat similar to the drone racing league, where you have these obstacles that the drone is trying to avoid colliding with, and then it has to sort of follow some path throughout the sort of like maze environment. But one thing you'll obviously note is that the current autonomous systems are not quite at the level of the humans in terms of the speed, but this has been a very active area of research that's improving quite impressively. And so if we look then at that configuration space for this robot, so as I was mentioning, so this is 6 degrees of freedom. So you've got X, Y, Z, so the translational position and then the orientation, so the roll, pitch, yaw. And so correspondingly, this would have a configuration space of what's called SE3. So it's Special Euclidean Group 3, which is the Cartesian product of R3 with SO3. So SO3 denotes the special orthogonal group 3, which corresponds to 3D rotations in space, and then R3 corresponds to the 3D translation. And so together, this SE3 group then represents the group of homogeneous transformations within 3D space. So our forward kinematics, for example, that we've been working with has been working with these homogeneous transformations. So let's now look at a larger scale robot, one that we've seen a few times in this class so far, and that is the fetch robot. So let's describe the configuration space for our fetch robot, and to make it just a little bit simpler, let's say that we ignore the grippers. So the first step that we want to take to define this configuration space is to enumerate the degrees of freedom. So to do that, let's think about each of the different joints together with the base in describing the degrees of freedom for this robot. So this figure here denotes and describes with an associated name each of the individual joints, and then has a corresponding arrow to denote whether it's a rotational joint or a prismatic joint. And then the base also has two arrows to denote that it can revolve, so rotationally, and then also translate along the ground with a forward arrow. So I'd recommend pause the video here and give yourself a chance to try and work through, first of all, just counting up how many degrees of freedom there are, and then describing the type of each degree of freedom, and then using one of the algebraic groups that we've looked at so far to represent each of those degrees of freedom to build up the configuration space. So I'd recommend pausing the video here, trying to work through those steps, and then resuming the video to check your understanding with the solution that we arrive at. All right, so now that you've had a chance to pause the video, let's start out by looking at how many degrees of freedom there are. So if we ignore the grippers, let's start with the arm, and we can see that there are a total of 7 rotational degrees of freedom within the arm. Then we can look at the neck, or the sort of head of the robot, and we can see that there's 2 rotational degrees of freedom there, so we're up to 9 degrees of freedom. The spine itself can translate up and down, so we have then a 10th degree of freedom. And then finally the base, because it can translate on the 2D plane, there's 2 degrees of freedom, and then that final rotation of the base would be a 3rd degree of freedom for the base, which gives us a total of 13 degrees of freedom. So if we write that out, we have 13 degrees of freedom. So we said 3 for the base, where that group we could think back to the case of our turtlebot and see that could be represented potentially by the group SE2. We had 7 rotational degrees of freedom in the arm, which we might think could be represented by T7. We then had 1 translational degree of freedom in the spine, so we could say R1 to describe that. And then finally 2 rotational degrees of freedom in the neck or the head, which gives us, or which we could think of representing with T2. So in total, we might think that the configuration space could be described by the Cartesian product of SE2, T7, R1, and T2. But one caveat that we didn't consider, and that might lead this to being considered sort of a wrong configuration space, is that for the revolute joints, and also for the revolute joints in the arm and on the neck, we didn't consider joint limits in describing that first configuration space. And so the caveat with the torus group is that it doesn't have a sort of natural way of incorporating joint limits. So we might prefer using the real group to represent those degrees of freedom for its ability to kind of easily incorporate joint limits. So instead, we might think of representing this configuration space as SE2 cross R10, where we would have then all of those rotational joints represented by the real group. But one downside, or one thought with this, is this question of like whether or not we could treat R10 as being a vector space. And so, because this will be useful in a number of the algorithms that we want to consider when we want to be able to operate with and kind of compute with configurations within configuration space. And so the answer to this is, in the context of configuration spaces for our robots, no, we can't treat R10 as a vector space because it won't be closed under addition or necessarily scalar multiplication. But we could sample from the configuration space using vector operations, even if it's represented in R10. However, this is still not quite right. There's still one thing that we've left out, which is for the rotational joints along the arm, not all of them have joint limits. So if you look, for example, at the URDF file within your Knievel stencil for the fetch robot, you'll see these joint limits expressed, where actually it turns out that 3 of the joints along the arm don't have limits. And so correspondingly, for those 3 joints, we can represent them with the group T3. So what we'll end up with then as our configuration space for the fetch is what's shown here. So we'll have SE2 cross T3 cross R7. So another example from our Knievel stencil that we could look at is the MR2 robot. So once again, I'd recommend pausing the video here and trying to work through this example. After going through that more complicated fetch, the MR2 should certainly be should certainly be doable, where to start with, the process is to first define the number and type of degrees of freedom on the MR2, and then for each of those degrees of freedom to express it within one of the algebraic groups that we've looked at so far, and to consider the possible joint limits or the type of the degree of freedom. So now that you've had a chance to think about this for yourself, let's step through it. So the first thing we can do is we can observe that there's 8 degrees of freedom for our MR2. So if we look at the joints, so they're highlighted as the yellow cylinders. So we have 5 rotational joints along the arms, and then the base of our MR2 can translate within the plane and it can rotate. So there's an additional 3 degrees of freedom. So in total we have 8 degrees of freedom, where we said we had 3 in the base, where we can recognize that those 3 can be represented by the special Euclidean group 2. And then the 5 rotational degrees of freedom in the arms can be represented by T5. And so the reason that we can represent them using T5 is by remembering that for our MR2 robot, there's no joint limits expressed for any of the rotational joints. And so one question then to ponder is whether or not we could treat SE2 cross T5 as a vector space for the MR2. And so this is a good question to think about for a bit. And I would say to some extent it sort of depends on whether or not we consider this to be the full configuration space. So it would be closed under addition if we ignore the environment and we ignore potential collisions with the environment. Then every potential vector within that space could be considered a valid configuration. But if you want to incorporate collisions, then I think you could make the argument that this would not be a vector space for our MR2. So a few other configuration space examples that you can think about. So one would be the Robonaut 2, for example. And then another interesting one to think about is the PR2 robot. But I would add on to this, there's a few other robots in our Knievel stencil. So the Baxter robot, for example, that you could also think about and work through offline. So now that we understand how these algebraic groups can be used to describe configuration space, let's think about how we can incorporate the robot's physical geometry with our definition of configuration space to model our systems more completely. So in particular, the distinction that we want to kind of draw some inspiration from here is the difference between configuration space and workspace of our robot. So to kind of emphasize the difference between these two concepts, let's think about the physical difference between the point robot and the turtlebot. So the left-hand figure is showing the workspace of a point robot, whereas the right-hand figure in this slide is showing the workspace of a turtlebot. And so the key distinction between these two setups is that the turtlebot has a physical geometry associated with it. So the actual structure, the actual mechanical pieces of the turtlebot exist within the workspace and are therefore going to affect what the valid configuration space will ultimately be. And so when we think about defining the configuration space for the valid poses that a robot can take, we have to incorporate this robot's geometry, right? And so if we think about this turtlebot, it's large. So another way of saying this is that the turtlebot is larger than an infinitesimal point within the workspace, right? So the turtlebot has some circular radius that takes up physical space in the workspace. And so as a result of that, as the radius of our robot increases, the resulting configuration space decreases, right? Because as the robot geometry takes up more of the potential workspace, the number of possible poses that the robot can be in that are valid, that are not in collision, will decrease. So the visualization on this slide, the top row is showing the workspace of our robot for various sized radius geometries, and then the lower row is showing the resulting configuration space where the invalid poses are grayed out. And so what you can sort of see in this conceptually is that as our robot grows in size, the set of possible poses within configuration space is decreasing. And so this motivates the question of sort of how it is we can convert from a point robot how does we can kind of convert a robot that has some physical geometry into a point robot conceptually, so that we can still define our configuration space in a way that will be easy to compute, right? Because it's very easy to consider at a specific point within configuration space, are we valid or are we not? And so to do this, what we're going to do is we're going to convert, we're going to sort of take our workspace definition and convert that into a point robot configuration space. And so an approach that we can take to do this is kind of conceptually is we can think about trying to expand the obstacles that exist within the workspace by tracing out the robot's geometry along the boundary of these obstacles. And the result of that is we'll sort of grow the portion of the space that is invalid, right? And then treat that as our configuration space for where we now think about it as being a point robot. And the result of that is we'll have modeled our robot geometry, but still be able to compute that configuration space and use it efficiently. And so a computational approach to actually perform this expansion is what's known as the Minkowski sum. So the Minkowski sum is defined on this slide. And so the idea behind it is if you have two sets, so we could think about these as being the two sets of points, where one of the sets of points is the workspace and the obstacles within the workspace, so the actual position in the workspace of obstacles, and the second set being the robot's geometry, so points along the robot's geometry. The Minkowski sum will be the result of adding every element of the first set to every element of the second set, where these two sets exist within Euclidean space. And so the diagram then in the lower portion of this figure is illustrating kind of visually what this Minkowski sum will look like in 2D. So if you imagine that set B is a robot geometry and the set A is an obstacle within workspace, what the Minkowski sum is showing you is you can kind of imagine sliding that robot geometry B about to the boundary of A, and that resulting set A plus B is the Minkowski sum. And so for the purposes of planning, we can use this technique to compute our configuration spaces for a robot to include its own robot geometry within the definition of the configuration space. So, for example, on this slide, we're showing on the left-hand side of the figure a robot existing within its workspace where there's a blue occluding object within the room. And on the right-hand side of the figure, we're showing the result of a Minkowski sum for this particular robot and this particular workspace, which can then be treated as the configuration space for a corresponding point robot within that represents this more complicated robot geometry in its workspace from the left-hand side. And so the resulting then Minkowski sum, so the resulting configuration space, which is shown on the right-hand side, could then be used for motion planning with a sort of more simplified algorithm that doesn't need to consider the robot's complex geometry. And so once again, so to sort of visually illustrate, one way that you can think about this Minkowski planning is to sort of imagine that on the right-hand side, so once you've performed the Minkowski sum, all of the occluded regions represent portions of the space in which the robot would be intersecting with an obstacle, whereas all of the spaces that are free of that occlusion represent poses that the robot would be taking that are collision-free. And so this Minkowski sum, just restated, it's an approach to identifying the non-intersecting robot locations or robot poses. And so you can imagine physically sort of putting the robot at every possible pose within the workspace and then checking whether it's intersecting or not to produce the result of this Minkowski sum. So that then valid paths can be computed by your motion planning algorithm, where the computation treats the configuration space as if it was a point robot. So given this example that we just looked at, one question that we can ask is sort of what does an obstacle look like in configuration space when we're using this approach of Minkowski sums? And so it turns out that the configuration space And the representation of obstacles within configuration space is ultimately going to depend on the rotation that we consider, the relative rotation of our robot and the given obstacle. So let's step through a couple examples to sort of understand what this looks like, to build up some more intuition about how these obstacles are represented within configuration space. So let's consider this workspace where the two gray rectangles sort of in the center of the workspace represent obstacles, and our robot takes the shape of this sort of planar rectangle, which is represented in red at the Q init pose and is represented in yellow at the Q goal pose. So if we were to use our Minkowski sum approach for defining the configuration space, let's first consider the case where we apply the Minkowski sum using this robot and this workspace for every possible robot position and every possible robot orientation. So these resulting green sort of oval shapes are representing then the positions and the poses within the workspace where our robot would be in collision, so that this result then can be thought of as the configuration space for our robot if it were allowed to take all positions and orientations. But this will change dramatically if we instead constrain the orientations that a robot can take to be only 45-degree angles. So if we can put that constraint onto our robot, but we still allow it to take any possible position, the result of the resulting configuration space will take this form, where you can see that there's now a much greater portion of the configuration space that would be considered valid poses for our robot. And once again, if we instead consider constraining our robot to be only at 0 degrees of rotation, once again the result of our configuration space will change to be what's shown here, where now there's actually a viable or sort of possible non-collision path that our robot could take from the initial position to the goal position that would not violate the obstacles within the workspace. So moving on from the case of our turtlebot and our point robot, let's move on to a sort of more interesting example of the two-link, two rotational degree of freedom arm, and let's ask how it differs from the point robot that we've been talking about. So the first distinction, and that's probably on your mind, is this torus that we've been talking about for representing the configuration space, right? So the T2 torus. So while the end effector of this planar two-link robot is still it still has a workspace that's represented in just sort of XY R2, the configuration space we described was with respect to this T2 torus. And so as a result, when we apply our Minkowski sum with respect to this T2 torus, we're going to have a sort of very different representation for obstacles in configuration space. So what's shown on this slide is what you would expect for performing this Minkowski sum approach within this T2 configuration space, where the grayed out portion of the configuration space on the right-hand side of the slide is illustrating the world obstacle 1, which on the left-hand slide in workspace is simply that circular obstacle. So you can see that it takes a very, very different geometric form once that obstacle is represented in the configuration space. And if we instead were to use these sort of oblong shapes, these sort of parallelograms and triangles, you can see that once they're expressed in configuration space, once again they take very, very distinct forms that are very hard to it's very hard to kind of reason about when it's in workspace, how those are going to transform into configuration space. And so that's one of the reasons why expressing everything in configuration space for our motion planner can be sort of a nice approach. So you don't have to go back and forth, right? You can just do motion planning in configuration space where both the robot and the obstacles are expressed in that shared representation. And this approach also extends to higher dimensions, although it becomes harder to sort of visualize and harder to really reason about at least for me. So for example, extending from the 2-link rotational planar arm to a 3-link arm, we can visualize resulting configuration space in 3 dimensions. So what's shown on the right-hand side of this particular slide is a 2D projection of the 3D visualization, where the red surface is representing that sort of manifold is representing valid poses valid configurations that this particular 3-link arm can take within its configuration space. So let's now generalize the concept of graph search that we had talked about earlier in this semester to this format of robot configurations that we've looked at today. And so the one approach that we can take, and the approach that we're going to talk about, is by using Costmaps. So Costmap is going to provide a weight on graph nodes within configuration space, where the weight is based on a set of factors. Right? So the cost that could be associated with each point within configuration space could be based on potentially the robot motion. So this could be joint limits or the smoothness of motion within that portion of configuration space. It could be based on collisions and trying to ensure safety, right? So potentially the distance from objects could be associated with the cost. And then finally, one additional approach, although there are others, would be environmental conditions that you might want to incorporate in certain portions of configuration space. So for example, certain areas of configuration space would be slippery or cause sort of traversability issues. You might want those to have higher cost so that your search algorithm can avoid those portions of the space. So as an example, let's look at how distance from objects could be used to form these cost maps in a way that would be useful for our search algorithms. So to produce a cost map based on distance, what you can do is your robot could compute the distance of each basically graph cell to the nearest obstacle boundary from configuration space and weight that cell higher if it's closer to a boundary. And so the result of that for a practical robot might look something like what's shown here, where the 2D plane that has these darkened portions is illustrating the cost map for then our robot, which in this case I think is a fetch robot, trying to navigate within the space. And so the goal then of navigating within the space is going to be to find a path of minimum cost along this graph that exists within this configuration space. And so this now should remind you of our search algorithms that we looked at earlier in the semester, right? So if we go back to that search algorithm template, we can now generalize it to this new notion of a configuration space, which is no longer constrained to simply adjacent squares of fixed distance, but is now defined over the more complete space. And so to generalize our search algorithm template, what we can do is we can substitute our notion of distance in the 2D planar case to now our notion of cost, where cost comes from this cost map. And so in particular, we could then apply our A* shortest path algorithm, for example, to find the path of minimum cost that would then result in our robot being able to move smoothly and safely, avoiding collisions within the configuration space. Now, one final nuance within this algorithm that we should address before we go and implement it in this generalized form is the sort of issue that we ran into in the case of 2D planar motion planning, which was we had a fixed graph of just north, south, east, and west adjacency cells. And so if we want a robot to be truly smooth, we might want to consider robots whose motion is not constrained in that fixed grid-like fashion. So the question that we're sort of dancing then around is whether or not our robot could maybe move simultaneously in multiple or any direction. And so it turns out that some robots actually do have this property. And so this property is what's referred to as being holonomic, or the holonomicity of a robot. So let's first maybe think back to our turtle robot that we've been discussing throughout this lecture, where we said that the turtle bot has 3 degrees of freedom, right? Because it has this 2D translation and then a rotation. But you could maybe make the argument that it really only has 2 degrees of freedom. And the reason for that is that in its physical actuation, it can only move forward and backward at any given instant. So it can really only move along 2 axes of the planar space. And so as a result, we would say that the Turtlebot is non-holonomic. And so the reason for that is that it cannot change its pose in all directions. So to sort of summarize that point, we have this slide. So both of the robots shown on this slide would be considered holonomic. So that is, they can change their pose instantaneously in all the directions of their configuration, right? And so you can see, for example, in the robot on the left, how it's able to move at any given instant. It's sort of moving along the X and the Y axis at the same time. Otherwise, if the robot can't do that, we refer to it as being a non-holonomic robot. And so these holonomic robot platforms, I would say, are becoming slightly more common to some extent in sort of these mobile manipulator settings. So there's a few here that are shown on this slide that we'll step through. These are really cool to see. They sort of look, to me at least, there's like a little bit of magic in how it is that they can, drive in these omnidirectional fashions. So the first one here is this synchro drive robot, which you can see is implemented in this kind of toy example. There's other examples though. So the KUKA U-Bot has these wheels that allow it to perform this sort of omnidirectional motion. And so you can imagine, for example, like in a warehouse setting, how this would be very useful to have the robot move very dynamically and not be constrained to sort of inefficient paths. You could have more efficient motion in this way. Another example then that's kind of fun is the DJI RoboMaster robot. And so this particular example here is from a race of these robots that's really kind of cool. Like they're like I said, I mean, to me at least, there's like an element of magic in seeing these omnidirectional wheels work, because they're just so fluid and natural. So then one other platform that we can look at here is this Killau platform, which is actually implemented with what I would kind of call almost feet. So it's almost stepping, but by combining the different actuation on the different individual kind of legs, it's able to achieve that omnidirectional motion. And so if you're interested, a nice external talk on this topic was given here by Raffaello D'Andrea. And so it's linked in the slides. If you're curious about this OmniDrive system, I would recommend watching it. It's very, very interesting. And so with that is going to conclude our lecture for today. So this then is going to lead into our next topic, which is how it is that we can search within these arbitrary configuration spaces, now that we've defined them, and how it is that we can build graphs to enable our search in these configuration spaces. So in the next class, we're going to be talking about planning using sampling-based roadmaps, where we're going to attempt to build a path from some initial state to a goal state entirely based on sampling within these configuration spaces. And so with that, thank you for watching today's lecture, and I look forward to seeing you in class this week.